So this is about norms. Now we need to briefly touch upon the fundamental spaces corresponding to a matrix. So those of you who have done linear algebra will recognize this very easily. Okay, so let's start with the most common subspace of a matrix. First, I would start with what is called the column space. Okay, so I'm going to split this like this. In plain English, how would I define the column space of a matrix? The space spanned by the columns of A, right? As simple as that. That means take all the columns of A and generate any linear combination of that. That is defined as the column space. Okay. Is there a very compact way of writing this? AX, right? So I'm going to define this as any vector y such that y is equal to AX. Is there any restriction on X? No, right? X belongs to Rn. Okay. What is the dimension of this space? M, right? Because A into X will become a vector of length M, right? So this is Rm, right? It's not going to be exactly this, it's going to be a subset of Rm because we don't know if we can cover all the vectors in Rm. It's not a given, okay? After we define the column space, the next intuitive space to define is the null space. Right? Right. How do I define the null space of a matrix A? Those vectors x such that A into x is 0. Right. So I'm going to define this as x such that A into x is equal to 0. Okay. So obviously the null space, every x is n dimensional. So the null space is living inside Rn. Okay. Now that we've got the column space and the null space, there are, you can see, two missing corners over here. So what should I write over here in the top left? Row space, right? Row space simply is the space spanned by linear combination of the rows of A. Rows of A are the same as columns of A transpose, right? So very analogously, I can also define this as x such that x is equal to A transpose y, okay? And is there any restriction on y? No, right? So y belongs to R what? M, okay? And x also obviously lives in Rn. Okay. What is left? Left null space. How do I define the left null space? All those y's such that A transpose y equal to 0, right? Okay, so these are called the fundamental subspaces of a matrix. Okay. There are two very surprising but very elegant properties of these subspaces. Can anyone mention at least one of them? So if I so okay, so a student has said that they are orthogonal. Which two are orthogonal? Column space and null space. No, I mean they are the wrong sizes. So if I take the row space and I take the null space, these are both vectors living in Rn. It turns out that these vectors are orthogonal to each other, right? So between this and this, there's a orthogonality relation. That's one thing. Between this and this, there is a orthogonality relation. Okay. It's not very obvious. It's easy to prove this, but it's not very obvious just from the definition that this should hold to. So this is one very important property. There are algorithms, optimization algorithms in signal processing which make use of this property to solve, for example, problems in MRI reconstruction. So you all familiar with MRI, right? There is a source which takes a cross section of your body image. They use these kind of properties to derive the images of your body. Okay. There's another final property about these two which is also very nice. Can someone tell me what that is?
Like the span of row space and null space will be R.
Will be? Rn. Like correct. That's right. So if I take the row space and if I take the null space together, they span the entire Rn. Right. So this is equal to Rn. And this whole thing is equal to Rn. Okay. So I can take a vector, any vector, write it as having a row space component and a null space component. Okay. Any questions on this so far? Okay, good. So the next, moving on from the fundamental subspaces of a matrix, the next thing comes to the eigen and SVD decomposition of a matrix. Okay, so let's start by looking at eigenvalues. Okay, so eigen decomposition. Okay. I mean, this is really obvious. I really don't need to define it, but I'll still say it. We all know what is the eigenvalue problem. Ax is equal to lambda x, where lambda is a scalar. Okay, actually, need not be. It can even be complex valued. You can have a real valued matrix with a complex eigenvalue. It can happen. Okay, and this is obviously only valid for what type of matrices? Square matrix, right? So A is square. Otherwise, this will become an illegal operation, right? A into x will give you the wrong dimension. So, it is A square. Okay. So, in optimization, there is a special class of matrices that comes again and again, which is a symmetric matrix. Okay. So, A, let's start with A is symmetric. Obviously, if it's symmetric, I'm implicitly assuming that this is a square matrix. Okay. If A is symmetric, there is a very nice result which states that a property of the eigenvalues. For a symmetric matrix, the eigenvalues are real valued, right? Eigenvalues right? The eigenvalues are real, okay? And let us say that these are lambda i's, okay? Corresponding to each lambda I, there will be some eigenvector, right? Eigenvectors. Okay, Qi. Now, when A is symmetric, you get the very famous eigen decomposition of a matrix, right? So the eigen decomposition in the case of a symmetric matrix is going to be written as, I'm going to write it in a form that you might not be familiar first. So what does this look like? I'm writing a matrix A as a sum of something, but let's look at each one of these quantities. First, sorry, yeah, I got this in the wrong place. Yeah. What does this look like? This is not the inner product. The inner product between two vectors was x transpose y, but this is more like xy transpose. So this is called the outer product. Which is a very powerful way of writing a matrix, okay? And summed over all of the eigenvectors and eigenvalues, right? You can see that Qi transpose, what size will it be? Qi is of what size? N cross 1. Qi transpose is 1 cross n. So Qi transpose is n cross n, right? what is, again, those of you who are familiar with linear algebra, what is the rank of AA transpose or QI transpose? It's rank 1. Okay, you will see all the columns or all the rows are just linear multiples of each other, right? So it has just rank 1. So in this notation, you see that I can write a matrix as a sum of rank 1 matrices. This is again something used extensively in optimization, machine learning, all of these things, particularly where there is application of sparsity happening. But we'll hopefully talk about that later in the course. So this is one way of writing it. There is the more common way of writing it is to write it in the form of product of matrices, which is going to be Q lambda Q transpose. Okay, what is lambda? Capital lambda. It's a diagonal matrix with okay, and Q is simply Q1 up to Qn, vectors like this. You can verify that once you open this up, you get the same expression over here. Okay. Is there something? There's something further special about this Q. Can someone remember what it is? It's an orthogonal matrix. Which just means that each column is orthogonal to each other. Right? Okay. One further simplification happens if matrix A is positive definite. What happens to the eigenvalues? They become positive. Okay. All right. So this was about your eigenvalue decomposition. Particularly, I mean, eigenvalue decomposition is used not just extensively in electrical engineering, but those of you who are interested in quantum mechanics will find these matrices appearing everywhere. Okay, it's just the nature of physics that you end up with symmetric matrices. So this was the EVD or eigenvalue decomposition. The other decomposition, which is of bread and butter for electrical engineers, is actually not just electrical, all of engineering is SVD, singular value decomposition. And it simply writes that, notice the similarity with the eigenvalue decomposition. Eigenvalue decomposition was very nice square matrices appearing everywhere. But in real life, your matrix A may not be square, right? So you're going to write this as U sigma V transpose. And something special about U and V, they are square, they are orthogonal. Square and orthogonal. People will refer to U and V as left singular vectors and right singular vectors. And what about this capital sigma? It has the singular values on the diagonal. It need not be square. In fact, if A is rectangular, sigma is going to be rectangular, right? So what are the choices like? If A is, for example, a tall matrix, so you will have sigma will be like this. Right? So S is a diagonal matrix, sigma 1, sigma 2 up to sigma n. Right? So I'll write it out fully. This is if A is tall. S if A is square, and S and 0 if A is fat. Okay, and S is simply a diagonal matrix of singular values. Okay. Now the convention that we will follow in this course, which is a very common convention in engineering, is sigma 1 is the highest singular value and sigma n is the lowest singular value. Okay. So if I don't say anything, assume sigma 1 is the largest, sigma n is the smallest. You notice that I can rearrange these sigmas and get a new decomposition, but it really doesn't matter, right? So this is always going to be largest. For example, if you use MATLAB, it will give you the decomposition with sigma 1 being the largest. Okay. Okay. And this singular, the matrix condition number which I had defined a few minutes ago, kappa of A, we will, you can see that you get a very nice expression. It ends up being sigma 1 by sigma n, ratio of the largest to smallest singular value. Okay. So this is something which again in MATLAB is just a simple command called cond, C-O-N-D. You give it like this and it will tell you what is the condition number. Okay. What is the condition number of the identity matrix? 1, right? So condition number actually has a property that the best you could do is a condition number of 1. Okay, and the worst is well, it's unbounded. Okay. Additional review, I'm pretty sure all of you know this, that for a square matrix, when I say trace of A, does everyone know what that means? Sum of diagonal elements. Is there any relation of that with the eigenvalues? It's the sum of eigenvalues, right? So this is summation of AII over I, which is also the same as summation of lambda I. Okay. Any other relation between some matrix property and eigenvalues? Determinant, right? So the determinant of A is the product of the eigenvalues. Okay. So that kind of brings us to an end of the review of linear algebra. Okay. So this is for you to kind of go back and look how familiar are you with it. Is it something that you can pick up by yourself, or you need to actually do the whole course? Yeah, that is something for you to assess. Okay.